Hello all, welcome to new video. This time I have brought something different. I'll be definitely continuing our CI/CD playlist, the ML in production. I'm working on it, but in the meantime, I came across something very interesting where I couldn't resist myself to record a video and explain it to you, all of the guys, explain it to you that what I have found out and how it is something interesting. Whosoever is very much interested in SciML, that is scientific machine learning, and GenAI. Currently, all over the buzz, over the LinkedIn, over the social media, over the industry is about generative AI. Everyone is dealing about transformers, LLM, agentic AI, RAG. And at the same time, the scientific machine learning is gaining its popularity due to its physics embedded knowledge, while neural network learns that knowledge across with the training stuff and predict more accurate result with less training time comparatively. So these two fields are currently being explored at very good pace. But I always used to think, what if there is an intersection of this? What if we could combine the power of scientific ML and Gen AI? The start of Gen AI was with transformers. And transformer, the main key pattern, the main key concept that drive this entire stuff is attention mechanism. As scientific machine learning is science plus machine learning, where the power of machine learning, that is neural network, is combined with the knowledge of physics. But the same way, can we have something that merges scientific ML with generative AI so that I can take the advantage of both the system and combine it? That was my question. I was going through some papers and then I came across Pinsformer, that is physics informed neural networks plus transformer. So isn't it interesting? Pins, that is physics informed neural network plus transformer. I find this something very interesting where I wanted to have the power of generative AI and scientific ML into one model. And I wanted to solve some mathematical equations that will definitely that will definitely outperform the disadvantages of traditional pins. So now, what is Pinsformer? This all will be studying and will be going through in this video. What is Pinsformer is not something we'll stop at. We'll see the paper Pinsformer. We'll try to understand what authors are trying to convey. Then we'll try to understand the results. We'll try to understand why Pinsformer are better than pins and what the key foundation architecture change or modification that has been made is responsible for this. Secondly, I have implemented this Pinsformer from scratch. At Visuara, you have saw many things that we implement from scratch because we believe if you have the understanding from the start to end, if and every each and every point, if you know out of the model, out of the architecture, then it becomes very easy for you to sustain in long run and develop something that is very impactful. That's why we have already many things on our YouTube channel and our other platforms, our portal that are from scratch, like Neural Network from scratch by Dr. Raj Dandekar and by Dr. Shri Panat. Then we have LLM from scratch, a very popular, a very hit a very hit YouTube series. Then recently we have launched book as well, that is DeepSeek from scratch. So you can understand that we have a lot of different stuff that we are integrating into our AI accessible mission. And we even have reinforcement learning from scratch. So this all things we like to deliver to you from scratch, where we ourselves even learn something new while we go through this. Similarly, for the Pinsformer as well, I'll be following the same steps and we'll be seeing the practical implementation from scratch. I've actually spent 2 to 3 weeks on implementing things from scratch. I'll be going out with some things just after this, and you might be saying me, Prathamesh, was it really needed to invest 2 to 3 weeks where they have already their GitHub repo? You could just download it, or you could just clone it and run it. I'll tell you what actual challenges I faced when I decided to implement it from scratch with just paper knowledge. And then I'll tell you how this actual qualities help us in doing a very proper research. Because when you clone and when you try to run it, you get a proper understanding. But the problems that actual author might have faced, you just read it, you didn't actually experience it. But when you will try to implement that from scratch, you will definitely find some difficulties which actually author has mentioned and some which author has not mentioned that might be just because of you are finding it difficult to implement or you want some more clarity on that so that you again revisit the topic, and that's why how you get motivated to do some research in the same field. Even while implementing from scratch, it is very important to know that we actually have a proper conceptual understanding, and same for that I'll be following here. I'll be explaining you all the concepts as well. Then we'll be moving towards the implementation part. And when you implement it from scratch, you might get some ideas to actually change the architecture and to make the architecture more effective and build some new architecture over this. This is how we pass on our knowledge in the research community, in the research domain. So now let us begin. So, what are actually physics informed neural network? Let us first ask Google itself. Physics informed neural networks, they are also known as PINs, are a type of neural network that integrate physical laws such as differential equation directly into their learning process. Unlike traditional neural networks that solely learn from the data, PINs combine data driven learning with physical constraint. So now you just think of a loss function that is for your neural network. Now you had one more loss function in the learning that is driven by the loss, the physical loss of the equation. And that's how the SciML works basically. So you could see we have this Navier stroke, and we'll have the experimental data loss, that is V actual minus V experiment. So this is how a basic physics informed neural network. We have a lot of other videos as well available where you can actually learn physics informed neural network from scratch. And if you're new to this, you could go back to that video. You understand the concepts. Though I'll be explaining you a brief of this in the upcoming video, but if you want to have a detailed understanding, you would just go back to the playlist and then you could come back after you finish neural network, physics informed neural networks. Now, what we are gonna cover in this lecture, we're gonna cover the Pinsformer architecture. But since now you saw the pins, then we'll see what is transformer. It's a AI overview. I didn't specify the exact transformer. I'll say transformer and machine learning. Probably I'll get something which I expect you to tell with the attention mechanism. So, transformer are powerful neural network architecture in machine learning and primarily known for their use of self-attention mechanism. The paper attention is all you need is a very hit paper, is one of the most cited paper. And what I wanted you to focus is two terms. First, when you have physics informed neural network, you don't just have a data driven learning, you embed the physics laws into that. That is one point. Secondly, is the self attention mechanism from transformer. So now when you try to just deliver new architecture that is Pinsformer, so what are the two things that are being combined? That is attention mechanism and the physics embedded learning. These two things are being merged to solve the existing differential equations like Navier-Stokes, like 1D wave, 1D reaction equations, or many more complex equations as well. So this is what we are gonna see. Then, how I came across this paper, that's a very interesting story. I was referring to ICLR papers. I wanted to check the previous ICLR papers. And since we have a very good record this year for publishing at a lot of many different places, so we are trying to search for good venues as well for the future our candidates, because we want to submit our candidates' work to at very good place. And I was going through ICLR papers and Europe's ICML and very, very good conferences. And what happens is nowadays all our collaborators and researchers, they want to work with the merge of SciML and GenAI stuff. They asked me, Prathamesh, why can't we combine GenAI and SciML and do something very interesting? And I was thinking about this from a long time, and that's why I keep searching for this different concept, different papers that are being out through Google Scholar and all. Then on ICLR website, I came across this Pinsformer, where I thought that this is something which I could definitely start with going. And as you can see, this is the like International Conference of Representation Learning 2024 paper. And when I started to go through it, initially I was very much confused about how actually I'm going to implement this. And the main thing which I did was I went through this paper two to three times before I actually implement. You could see the Pinsformer transformer based framework for physics informed neural network. And as I go through the paper, what excites me was like they mentioned that there are some traditional limitations in physics informed neural network, such as sometimes the conversion takes a long time. Then it takes for the complex PDEs, it's difficult to give a solution accurately. With the less time, it takes a lot of resources. And attention mechanism somehow was not convincing me because attention mechanism is generally used for language tasks, and to use the concept that is used for language tasks to the concept of physics language was something very new and was something very interesting, isn't it? That the language of attention mechanism is being used for physics. The main concept that revolves around natural language processing is now being used for physics. Is something that is very exciting thing when it comes to AI. We definitely have a lot of different stuff can be applied to different things. Like earlier transformer paper was for the language translation, but then it got like deviated, not actually deviated, then it got a lot of new applications. And in the same way, this attention mechanism, these authors have done great work in bringing that to the physics informed neural network. And then I started going through this paper, and there are some results which I actually liked it. So this is the brief architecture. I will go through each block of this in detail in the upcoming sections, no worries. But you could see they have a pseudo sequence generator, spatio-temporal mixture, the MLP multi-layer perceptron. They have encoder, decoder, that is the transformer core thing. That they have output MLP and the neural network output, and they approximate the solution. Then they have a modified loss function that definitely would have been because it has a physics loss, and now you're integrating the attention mechanism as well. And then they have their own new function, the custom activation function, that is wavelet function. We'll go through this in detail, its section, but I'm just trying to connect you dots so that you find it very easy when you go ahead of the video. And then you would see the experimental setup is done very nicely. I would like to show you results. Sorry. You would see the predicted with the Pinsformer prediction and the actual Pins prediction. There's a lot of difference, and Pinsformer is actually overshadowing the other existing methods. Even you could see when I implemented this from scratch, I'll show you some results. You could see actually I got for the Navier stroke, the predicted was this, the Pinsformer one, and the exact solution was this. So you could see the predicted matches was exact. Absolutely, with some minimal error, and the absolute error was very low. So this is some interesting things to be worked on. So this is the paper which, if you want to read, I'll attach it in the description as well. Kudos to the authors for giving us such a wonderful framework, which I think has a potential to definitely transform into something bigger. And we actually have implemented this, so we have tested how powerful is this, because it's not something like we are just claiming it out of what we read. We actually implemented it from scratch from our end and match the results with what actually authors got. And then only we are bringing this out to you. Then this is the GitHub repo. I'll share the link as well. You could go through this GitHub repo and understand and implement the stuff. I'll be sharing my GitHub repo as well with you where I implemented from scratch. And I think that might help you as well. But if you want to have a standard one for the implementation, I think there's one is perfect for that. And I'll explain you the code files, I'll explain you the code snippet so that you would actually understand whatever thing is there in this GitHub repo. And it would be easy for you to implement it. And then we'll be seeing what are the future applications and where we can extend it. So this is very interesting stuff, I think, and we should definitely go ahead with understanding, and that might give you some idea to carry forward your own research as well. So I'm very excited to explain you which concept and the coding implementation. I actually faced a lot of difficulties in the training time and then the hyperparameter tuning, so, and writing an encoder decoder block, wavelet functions was something which I could actually comparatively easily understand it, and I could easily implement it. But the idea of introducing such activation function as wavelet is something which is very appreciable. And even we can think of some new architecture, a new activation function. Feel free to comment us below. Like if you have some suggestions while we go ahead for improvement, we would definitely like to understand your thoughts on this as well. So now let us start understanding the Pinsformer architecture. Let us see the Pinsformer architecture. Before that, let us summarize what we have just discussed till now. Pinsformer overcomes the MLP-based physics-informed neural network limitations, such as slow convergence, poor generalization, and difficulty modeling complex spatio-temporal PDEs. Consider you have the PDs and you have that in an isolate system. You just have point in that isolate system x comma t, and you wanted to predict something. With normal mathematical formula or analytical solutions, you can definitely do that. But if you wanted to predict something which is based on this, then using this for a continuous thing, or to use this for the temporal dependency problems might be a tough case. And for that, we are integrating, the authors propose to integrate the attention mechanism so that it could actually learn from spatio-temporal structure. And that's why this architecture is getting quite famous. Next, as I mentioned you earlier, that it integrates transformers with wavelet activation, enabling stronger attention over space-time features and more expressive function. You have TANH, ReLU. These are the activation functions we generally heard of. But they propose the new activation function, that is wavelet activation function, because the most of the time, sometimes PD shows oscillatory behavior. And when they show oscillatory behavior, what a function comes to our mind is sin x or cos x. So they somehow make a linear combination of these functions like w1 sin x plus w2 cos x and call it as new activation function so that it would match the ideology, it would match the pattern that PDs generally has. And that's how it could integrate with transformer and learn the periodic thing as well as the function as wavelet function, which is consist of a linear combination of sine function and cos function. Now let us understand the transformer architecture in detail. Let us understand the Pinsformer architecture in detail. We'll go step by step. And first, I'll show you this brief diagram. Then, for each block, we'll spend some time. We'll understand how it is and why it is so important. First, you have raw input xt. Consider x as a position, t as a time. These are the two. Like I have two dimensions, or I have two numbers as an input. Then I have a pseudo sequence generator. As I told you before, that isolate system or just one data point is not enough for me if I wanted to use transformer in physics informed neural network. But I have the x comma t as the solution and I want to extend it. So that's why I generate a pseudo sequence based on this x comma t for further case steps. And that's what a pseudo sequence generator. Then a spatio-temporal mixture. Now consider I have x comma t. The dimension is 2. All the hidden layer size which you used in your transformer architecture or in your any other LLM stuff, or a basic neural network structure, you might find you have a 128 neurons in a layer, 64. So you basically play with 32, 64, 128 dimensions. Just having a 2 as a dimension, it may be difficult for transformer attention mechanism to actually learn some patterns out of it. And that's why we need to transform the latent space into bigger latent space. What I mean by latent space is the input form into such manner that is something out of which we can derive some embeddings and we could actually learn. It's not something a normal x comma t, it's some transformed input form. So if I have this 2, I would transfer it to 32. This might be the one of the case of spatio-temporal mixture, that is MLP. Then you have encoder and decoders to capture global relationship, decoder to capture local relationship. Then we have a output layer, that is MLP, and then we just approximate solution when it passed through output layer. Now let us understand each of this in detail. First is pseudo sequence generator. Now we'll see one projectile motion image. So if I'm throwing a ball from one direction, like from here to here, I could actually calculate, you could see this, I can actually calculate the UX, UI, the velocity in the X direction, velocity in the Y direction with the acceleration. I could actually calculate range, height at one point because I have this trajectory. I have this trajectory with me, and that's why I could calculate it. Now, if I don't have any information, if I had just this point, and if I didn't have much information, I probably could not predict much at this point or this point. Consider I don't have much information. I just throw the ball and ball is here. I don't know what is the drag and what is the air pressure or whatever the thing. But if you see this ball is just here, no projectile motion or no trajectory, I just throwed it. There are possible chances that it might just fall immediately. It might fall after certain range. That distance depends on the velocity it was thrown at and all other factors that are involved. And that's why we need to take care about the entire projectile motion to find the height of a ball at particular point or whether that will land before we calculate the height. So that's what is all needed. And that's why if you have this 2, 3 blueprints, or if you could just have this 2 points, one is this, one is this. If I had this two, I could probably calculate most of the other things that are required. And if I could get similar things for my transformer in the Pinsformer architecture, my probably attention mechanism function would be solved mostly. And what I have to do is, that's why I make a pseudo sequence generator because I don't have a real sequence of out of that. So if I have x comma t for the next k steps, that k is again a hyperparameter, you'll have to experiment with that according to your need and according to your equation. So for that t, I'll have first as xt, then I would have x plus t plus delta t, then x plus 2 delta t, and such that I'll create a pseudo sequence. Because attention mechanism, if someone is new to this, I'll try to tell you attention mechanism, if you're having a sequence like you are a doctor at hospital. So what attention mechanism will do, it will take care, if you're just taking doctor as a word, it will take care of this, the you doctor relationship, our doctor relationship, that how each word is getting affected by this doctor word, it will take care. It would not left out you, it would not left at a, it would not left at, it would not just focus on hospital. It would definitely calculate the score between all. There might be the case that the correlation score or the score or the similarity that might be maximum for doctor hospital because they are probably falling in the same domain. But it is not that we are neglecting this because there might be the case that this are actually calculating for a novel or for a book story. I could actually figure out this you is someone a doctor that is being referred, but at this point it was not looked at, but in future I might need it. That's why this long-term dependencies need to be taken care of. And this is how attention mechanism does. But when you want to use this for your physics stuff, your x comma t is not sufficient for that. And then if I have a sequence and x t plus delta t, then x plus 2 delta t, and so on till k minus 1 delta t. I have a sequence. And then with that sequence, I could definitely get a long range dependencies, short term dependencies. So that's why this would be important for our encoder decoder as well. This will bring causality as well. Suppose x comma t considers as your past value. If you're adding delta t for the k steps, you are definitely going to the future. So this is adding causality. So like the projectile motion example which we saw, this is very important, and based on that, we'll be calculating our things. Probably this won't take much loss. You might think this is pseudo, this is not real one, this might affect the results. Probably this won't much because your initial baseline is not randomized. You take a x comma t, which is actually for the solution. There's not something that you randomly choose x comma t and you just add delta t over it. We need some sequence, and it's based on one concrete base point. The entire sequence is not real, it's pseudo, but it probably won't give you the false results. Now, next is spatio-temporal mixture. This mixture enables low dimension spatial and temporal features into the high dimension latent space, enriching the data representation. So we'll just check for the temporal structure in machine learning. So refers to sequential ordering and time dependent relationship with data. Okay, we'll see if there are some good images. So, okay, I have some recurrent neural networks which believe on the temporal thing, then spatial structure in machine learning. So, the spatial one refers to a method model used to represent, analyze the geographical or physical arrangement. Now, I think it might be clear to you that why spatio-temporal mixture is being used. What we are using? We are using Pinsformer, that is physics informed neural network. Pardon me for my handwriting. I'll definitely try to work on it. Plus transformer. Now, transformer, if you remember, we usually deal it with generative AI stuff. I mean to say language translation. So it has attention mechanism. I have repeated it quite a few times now. So this would deal with the temporal structure. It needs the like sequence dependencies. Consider you are a doctor at a hospital. So that doctor and hospital has some relation. It needs to be in sequence. The sentence is not you are a hospital at doctor. This is not making sense. So this all comes with the dependencies in the sequence. And we need a time dependencies as well. So I need a temporal thing. But you have a physics informed neural network. That's why the position matters as well. I have a physics that is governing the entire equation. So if I take x comma t points, you could actually say if x is a displacement and t is a time, or x denotes the distance or t denotes the time, I actually need something that is spatio-temporal and it analyzes based on this x and t. But if I want to give it to transformer, encoder or decoder, don't you think that's not enough dimensions to be done? Because these are two, whatever the complex relationship it has to learn, the transformer is quite a huge architecture by itself, by the encoder and decoder stuff. But if you actually try to bring it with just two dimensions and input, and if you wanted to learn the complex PDEs, then this is not sufficient. This is what authors are trying to say. And that's why we need to transform this input dimension. We need to map this, convert this into high dimension latent space. What I mean to say is, if I am having x comma t, I perform certain operations such that my new input space dimension is 32, 64, or 128. I'll perform some operations such that I convert it into zi, where Zi belongs to. There's 32, 64, 128 dimensions either. I wanted to increase the dimension so that it becomes complex and learns different patterns and actually gives me a very, very good solutions for my problem statement. That's what is the use for pseudo sequence generator and spatio-temporal mixture. Next is encoder and decoder transformer. Let us now see the encoder decoder architecture. I guess we have studied the spatial and temporal one quite well before as well. And now let us see about this encoder and decoder one. Basically, encoder decoder in the Pinsformer architecture. This encoder basically focuses on learning global relationship, whereas decoder focuses on learning like local relationship regarding boundary conditions, initial conditions, its impact over the time and changing position. So this is what encoder and decoder behave. Let us now understand that in much. So encoder and decoder transformer. At the heart of architecture lies the transformer block. As I have told you before as well, the encoder captures global dependencies across the pseudo sequences. And what do you mean by global dependencies? Now consider you have the wave function and you have some wave that is like this. And now this point and this point, you wanted to find out the direction of it. So this direction comes along with the long play. This is across the x direction. But this long range dependencies or the global relationships I wanted to find out. And for that, the embeddings that I have formed with using spatiotemporal MLP would help me to understand this relationship, and the attention mechanism would come into picture. Now I'll show you one image. So like this is the way one. I just took it from random assignment workbook, and these are some directions of the wave in different coordinate system. And here I want this to be considered while predicting the future wave propagation or something, and that's why this encoder will help understanding this direction stuff. Now, I wanted to study the boundary relationships like boundary conditions, initial conditions are very important in physics. As you saw in the trajectory example of projectile motion, whatever the initial velocity I mentioned over there, based on that, whatever the acceleration, whatever the drag would be there, based on that, the values of the future predictions of the velocity, height at the ball would definitely change. And that's why this initial conditions, boundary conditions are very, very important. Whenever you define ODE or PDEs like Navier-Stokes, 1D wave equation, 1D reaction, at that time you will definitely come across the boundary conditions, initial conditions. In normal physics informed neural network as well, it is very important to define boundary condition, initial condition. And if you don't have it, we synthetically or we assimilate different variables to predict the most appropriate initial boundary condition, because on that your entire results would be dependent. So you could consider this as a one attention map. And if this is an attention map, for example, which we are giving it to transformer, don't link it with physics, but try to understand the analogy with this. So this all relationship. So this is the attention map, which is the core one. So this part would be deal with by decoder. So consider this as boundary condition. This is initial values, something like that. And this would be taken care by decoder. And the long global range dependencies would be taken by encoder. So this is why it is important in this Pinsformer architecture. And these concepts are directly derived from the original transformer architecture and are merged into this Pinsformer architecture. So this through multi-head attention, this layer enables network to learn both broad trends and fine-grained temporal behavior efficiently. As we saw in the image like attention map, so the details, small details around that point would be definitely learned, and global dependencies would be also considered. Then in the start, I already mentioned you that there one key innovation lies in introducing wavelet function. And why they have used this wavelet function is the authors think that the physics has a lot of oscillatory behavior into that. So you have the continuity, you have a lot of oscillatory behavior when it comes to defining PDE. And that's why if you use ReLU or TANH, then it would be hard for building the models, and you'll have to make them learn the physics. You'll have to make them to learn that oscillatory behavior. And the ReLU and TANH are generally not that useful to learn that oscillatory behavior. Here is the graph of the ReLU versus TAN. You could see this ReLU is basically for the values which are less than zero at zero, and for the less than one, sorry, for greater than one, sorry, greater than zero, it is that same value. And tan H, you could see it is slight a curve, but not an oscillatory curve exactly. So this lies from -1 to 1. But the PDEs or the ODEs which you'll use will definitely depend on the oscillatory behavior, whether it be wave, whether it be Navier-Stokes equation, the reaction equation. And that's why, what if we actually build a network that has physics already inside it while the training itself? Not to, it to learn that physics, the oscillatory behavior at a point of training. What we build a network that is already this thing embedded into that. With this ideology, this wavelet function came to picture. And instead of conventional activation like ReLU or TANH, Pinsformer uses wavelet inspired activation function. So this W1 and W2 are weights, and these are managed with respect to your problem statement. These are being optimized, and you can initialize with certain values, and then you can experiment for the most optimized version. Again, would come under the hyperparameter tuning. And this W1 sin x, W2 cos x, and this is linear combination of sine and cos function. And this is then included into your activation function instead of ReLU or TANH. Even you could try to experiment with some different activation functions as well in order to get good results. And if you want, if you have any suggestion like what you think could be the potential much more good version of this activation function, please let us know that as well. So this activation function, since it has sine and cos functions, it is smooth because it will be graphs would somewhere lie around the sine x plus cos x1, and then it would be differentiable, and it would be like Fourier like providing stable gradients. We'll have a stable gradients because of the sin x plus cos x, and it would have a better approximations of oscillatory physical dynamics. I think this was the main motivation from which we started, like why this is needed. And once you've done this, we are completed with this four steps: that raw input is done, pseudo sequence generator is done, spatio-temporal mixture MLP is done, then output MLP would be dealing with, encoder part we have done, and then we'll have the approximation once it passed to the output layer. But what about the loss function over here? How is that loss function? Because in physics informed neural network, the loss function, it has the physics loss included in it along with the neural network loss. The loss that comes from the ML stuff plus the physics included loss. This way, your physics informed neural network changes the loss function. But what happens in PINs is like at once you're trying to learn all physics. It's not a sequentially adding the physics loss. It's not at t is equal to 0, check for add this loss term and check whether it is going in correct direction. At t is equal to 1, you again add that loss and you check if it is going in correct direction. If it is too high, then optimize. This is not what it is done. It actually takes the entire term, entire loss, like physics from ML, sorry, loss from ML stuff plus loss from physics. Like this, you directly calculate the loss. What happens is this may take much time for convergence. This entirely would take more resources. But what if we add this sequentially, step by step? Because physics would definitely beyond it will go for the it will go for the time steps t, and at every time it would affect some position or it would change some speed or it would change some velocity. And for that, if we could add sequential loss over there, then it would be very, very important. So that's why this is very important. And that's why the change which they have done in this physics informed transformer model is like they apply a physics based loss function sequentially over the pseudo time steps. So by enforcing residual boundary and initial condition losses at each step, the model maintains physical consistency across time and achieves smoother convergence. So as I told you, it doesn't put all thing at once. It takes the step-by-step approach. So let us go to Pinsformer paper. Yes. So you could see actually the visualization of the loss landscape for pins. This is the left one, and the pins former the right one on the logarithmic scale. And the loss landscape of this pins former is significantly smoother than the conventional pins because of the sequential loss and the wavelet function. That's why you could see how this modifications actually prove to be very important in long run. At first, the idea may not be that convincing, or you may not understand the importance of that since we are just learning. But when you actually see the figures, when you actually see the values, you'll definitely understand the use of it. So that's why this the loss function, the sequential one idea is quite good. And definitely this entire thing contributes towards a good architecture. Now, when we'll implement it from scratch, at that time I'll make you understand each part of the code, different files as well. But there are some key code snippets I think we could just have an overlook over that, and that might be very helpful for you when we actually go for the implementation from scratch. The wavelet function, I think that would be very simple for you to understand that it would be W2 plus W1 sin x. So we'll write the sin s function and we'll have this weights W1 and W2 according to the neural network optimization. So you could say it blends the sine and cosine waves with learnable weights W1 and W2. So we have the init class. We'll all go through that. And if you are new to Python, I recommend you to go to the Python playlist, the Machine Learning Foundations, FML by Dr. Sridhar Panat. So feel free to go towards that Python programming lecture and then come back to understand this why the init has been written, what is the use of self, what is the constructor, and what all other stuffs are. If you are very new to this, I recommend you to watch that video and then come back by the time we go for the implementation from scratch. So this is self.w1 and self.w2. You are initializing and you're optimizing the weights, and you are taking nn parameter, and then first you are initializing it with 1, and it will definitely optimize it further. And for the def forward, since what the function is, this is cos x a plus b sin x. So this function value should be returned when we call this wavelet function, or we feed something over this function, and that's what we are returning as w1 torch sin x plus self dot w2 star like w2 into torch dot cos x, and that's what we are returning. And then the Pinsformer architecture. So what I'll try to tell you is we have this xt, the initial raw input, two dimension. Then we convert the embedding, or suppose 128 dimension. So this embedding, then what happens is then it goes to encoder, then it goes to decoder, and after going through that, it goes to the output layer, and then it gives you the approximation u x comma t. So this is the entire Pinsformer architecture in nutshell, and the same thing would be similar would be found in your code of Pinsformer. So let us see. See, as you saw that there's an embedding. So initial my input is x comma t. So I could see the linear one, and I get a linear embedding out of this where I transform this dimension 2 into higher dimension. Then I have the encoder one, then I have decoder one. We have the number of heads which we have to specify. This all things would come into the implementation part soon after this. And there I'll tell you how is the encoder class implemented, how is the decoder class implemented as well. Then we have self.linear, that is, we want to give a output. So that's a sequential output. Again, the sequence of the layers would be there. Then see, we have a layer one, neural network layer one. Then we impose a activation function to induce nonlinearity and to understand oscillations. We have waveact, which we have defined here, the custom activation function. then we have nn dot linear, then we have again wave act. So this is two layers followed by the activation function, and then the last one where we have the output layer. So this is entirely the init function in the class Pinsformer. And then we try to forward it. The forward class, forward function helps it to follow it for the iterations and just put it outside. The forward class helps us to reach at the final step. And you could see we can have a linear embedding, then we have an encoder, decoder, and we have the linear out. So the whatever this a small flow chart which I have mentioned at the side, that same has been written over here. So when we actually go for the implementation part, at that time, I think you guys would be very, very like curious, and you would be able to understand what each line of the code says, since you will have a rough idea of this. So now let's talk about some important challenges. What challenges I faced? First of all, the main challenge which I faced was paper understanding. I'll be honest, at first two iterations of paper, I was not able to understand paper completely. When I read it 3 to 4 times, I was able to understand the ideology and the concept behind it. Though the basic concept was clear to me with the title and with the one reading, but I had a lot of questions which was there answered in the paper itself. But since I couldn't capture it at one go, I had to read it again and again. And then I could understand each point. Like there's one, two, 3 points which I would actually refer you when we come for implementation part. And that time I'll tell you what actually I faced problem and where I was struggling to understand the concepts. And that's why I went through this paper 2 to 3 times. And the last time, then while implementing, I was going through, and to deliver it to you, I need to make sure I actually understand everything, what I'm saying. So that's why that was again when I was going through the paper. So the hyperparameter tuning was my main issue. The results which author got for the Navier-Stokes and for the 1D reactions. So that was not the same parameters which I could get the same results. So I'll go to the GitHub repo. Now we'll go for this demo one. In that you might have see the Navier-Stokes and the Pinsformer. So there, this is the entire architecture written. They got this low loss error value, and then their error p was quite less, and their exact and predicted were quite matching, and the absolute error is very low because they were matching. I got the same plots, but the values were not same, so that means there was some discrepancies actually there in the hyperparameter tuning. Like I need to change that something. So here you could see the in features are 32, out features as 512. So this all needs to be taken care. So when I implemented this paper and implemented this notebook, what I did is I changed this hidden one. I changed the model dimensions. I changed the number of heads. Because of what, it took long time to run. But for T4 GPU, it was not possible to learn. Then I have to shift it for A100 GPU. That comes with the pro subscription. But if you are using T4 GPU, you'll have to dedicate some more time for the training. It might use your entire resources as well, but and it might be a little frustrating, but you could actually try Kaggle as well for the free GPUs if you want to run this. Or feel free to use any other option that is best suitable for you. So these were the hyperparameters I have to change to in order to get this same results. Though the values were not matching exactly. It's not what exactly I got 0.2800. It's not like I got this 6.6 E minus 0.6 loss value. Rather, I got somewhere around 7 for this, but the range was same. Suppose if the loss value, error value is in the range of 10 raised to minus 6 with the some value of 6, then I got it around 7 into 10 raised to power minus 6. But plots were quite matching, and error plot was not that different. So actually, I could manage to get proper results as what authors got in the paper. And that's why the hyperparameter tuning I have to spend a lot of time, because I was quite lucky in 2, 3 iterations I could get it to. But then I'll have to spend a lot of time over a training that it takes 2 hours to run, and then I'll have to wait. And if it still doesn't give me proper outputs, then I'll have to shift that as well. And that's what is the major issue which I faced a challenge. Secondly, the training time. They use CUDA 2, CUDA 3, but I'll have to use normal CUDA. And for that, the T4 GPU was working well for the 1D reaction. It worked well. It took very less time comparatively, like 14 minutes around. But for 1D wave and for Navier-Stokes, T4 GPU was taking a very, very huge time, and for which I have to shift to A100 GPU as well. And that is the second important challenge which I faced. That was GPU and CUDA issues, than hyperparameter tuning, which I have already informed you before, and then the training time, which we have discussed that it take huge training time. Even with the A100, it took 1.5 hours for Navier stroke. So I'm like little skeptical about that. If I have a very complex PDE and if I try to run over there, I doubt it would take a huge training time. But okay, it's fine. We have to improvise architecture as well if we could. And in the ML stuff, the training time is something it definitely takes. There are problems which take much more training time, but definitely we could manage. But it's very important for us to first understand this so that we could think of different ways to improvise this. So now let us see the last theoretical part before we enter into implementation, that why and how Pinsformer beats physics informed neural network. The wavelet activation could serve as drop-in replacement for standard activation, as we saw that to bring the oscillatory in the training part itself rather than making it learn later. The authors introduced that wavelet function. So this wavelet function is a good addition, and that makes Pinsformer significantly different from normal pins. But as name transformer comes, so what majorly changes the Pinsformer from pins is multi-head attention mechanism that transformer brings to encoder decoder. So that is very important. And then a pseudo sequence framework is very important because we wanted to have a causality and we want to learn that causality so that we have a proper predictions in future. But that is again a necessity for transformer, because if we want to use multi-head attention mechanism, you need to provide some sequence. And to generate a sequence, if you don't have the enough truth data, ground truth data, then you have to generate it synthetically, or you have to generate a pseudo data. And for that, you will need a pseudo sequence generator. Then integrating the Pinsformer with neural tangent kernel. This has been done, but we are not discussing this entirely in this. We are focusing on basic Pinsformer. But you can definitely go to paper and see how this Pinsformer NTK has actually performed well. And it has adaptive sampling or the meta learning, the hybrid model with Pinsformer, they think can get a good results. And I'll try to show you in the paper as well. You could see the 1D wave, the Pinsformer plus NTK, the loss value is the lowest for it. The error is lowest for it, and RMS is also very low compared to Pinsformer and Pins NTK. So this hybrid model is something is very very exciting to explore as well. You could replace this NTK with some other concept, some other model, merge it with Pinsformer, and you can definitely get a good results. And if you have some idea over this, please let us know so that we can actually help you for this as well. If you have any questions, you could just put it into chat. I'll try to answer. Now we'll be going towards the implementation part. I'll be taking my code as well, and I'll take a standard code of this GitHub lab, and I'll try to explain you each snippet very clearly. Then I'll show you the one practical demonstration of 1D wave, how I imported the files and how it run and how it actually take time. And that we'll see one practical demonstration of that. And that's how we'll wind up this one actually long video. But I hope this would be very useful for you. Now, we are going to perform a scratch implementation of Pinsformer architecture. So this is the GitHub repo provided by authors in their official paper. And it has checkpoint demo model folder, a README file, a standard practice for any GitHub repo. Then they have this utils.py file. then visualizing landscape.py file, and Python.py file. So we'll be going through this file. I'll give you a brief idea how we are gonna proceed. So this is the Pinsformer file readme, and there they have given the files which if you want to run for visualization, they have given some tips and like commands to run. What we are trying to do is, what we'll do, we'll go for the model one. In the model one, we'll try to implement this Pinsformer.py. You could see the pins implementation of Pinsformer. This Pinsformer implementation will be doing from scratch. As you can see, I have explained you this before as well, this class Pinsformer snippet. Along with that, the wavelet function we have already studied. We'll implement this and we'll understand this from scratch, and we'll go through each line of the code. I'll try to explain you in brief that what we are trying to do in this, what authors are trying to convey. And we'll be taking the util.py file from the authors itself. We'll be not coding it from scratch. We'll be taking this from the authors, but I'll still explain you what it is completely doing. Because if you could see, utils.py plays a very, very important role, because here they're importing the get clones from the util file. So we'll implement this pinsformer.py. We will take util.py from authors. Then on this demo notebooks, we'll try demo on 1D reaction. I'll show you the results for 1D reaction, 1D wave, and Navier stroke as well. But I won't show the actual implementation that is live for all three because it will take too much time. I'll tell you the steps how you can similarly do it for others as well. But I'll show you this 1D reaction Pinsformer implementation, and we'll try to see if we get results that are similar to author's results, so that you can actually believe in this. You could see the residual loss, boundary condition loss, the initial condition loss, and overall training loss is there. Then there are some hyperparameters which we could definitely change, like hidden, then number of layers, then number of heads. This we are power to change the hyperparameters, and how results are affecting with the change of hyperparameter tuning. We'll see all of this for our implementation, and that's how we'll perform the implementation part. So I would like you to go through this GitHub repo. I'm sharing the link in the description below, and you could just download this util.py, and in your Google Colab file, you could just open your Jupyter notebook, or you could just in a VS Code, or even it is completely fine. You open .py file, .py or .ipynb, both are okay for us, no issues. If you wanted to have a proper GPU running, so you could definitely take a Google Colab, because it will be easy for you to import those file and use the T4 GPU or A100 GPU. And I'll tell you a few more things before we proceed ahead. Firstly, we'll go to Google Colab. When we'll go to this Google Colab, this connect option is there. Let us see where it is getting connected for now. Now Google Colab is available in VS Code as well. The extension is there. You can still do it. If you face any difficulty in that, so for now we'll stick to the Google Colab. So this as well. So you could see here this normal CPU is connected. You have to go to change runtime. And since this is a pro subscription, I have option to choose A100 GPU. You have to click OK over there. I'm canceling because I want to show you different stuff. But if you want to save this, you could just click OK A100 and save. After that, only make sure you write the code, because else all the files brought up locally would be deleted automatically if you change this runtime in middle. So make sure you follow that. If you are using normal Google Colab, then the T4 GPU would be definitely available to you. So you just click on T4 GPU, OK, and then save. So this is how you could actually do it. And then we will definitely start coding the stuff. I have created a Google Drive folder as well, where there is implementation from my side. I'm sharing GitHub repo so that standard implementation is with you. I'll make sure that you run that as well, and that can be used as standard one. But if you want my this folder link, please let me know in the comments by letting me know if you are interested to see the Google Colab folder, which Drive folder, which I have maintained. I've actually included this summary document as well. I'll be honest, I have taken help of AI tools to generate this documentation summary as well. Not completely, but for some extent, so that the language is being maintained. So please let me know if you wish to have this documentation as well, so that I could share this with you. And you'll actually able to see what hyperparameters work for me, what hyperparameters are working for you, what CUDA version is working for you, what CUDA version worked for me, and what was author's CUDA version. Everything would be clear to you. So now let us begin with the Pinsformer implementation. What we'll do is we'll firstly go to Pinsformer 1. I'll download this util.py. Okay, then I'll go to this. I'll make a new notebook in Drive. We'll first name this file. Yeah, Pinsformer, then connect, change the runtime. I'll make it 800 GPU. Then I'll upload some files. So once this is connected, I'll be able to upload the files. If you face some issues, you could definitely take the benefit of Gemini. We have now understand enough theory and we have seen some snippets as well, like WaveAct and Pinsformer snippet, that give us brief understanding of the code. Now what we are trying to do is we are trying to actually see the code which is implemented by the authors, and then we'll run this code as well. I myself have implemented this from scratch, but what I believe is I'll take this author's code, which is a standard one, and explain you this and show it you running. So I have copy pasted this code from their GitHub repo. I'll show you my implementation as well, but I'll tell you the source from where I have taken this code. I think I have repeatedly mentioned that before as well. I have taken this from their GitHub repo. I'll share the link in the description. So in the demo, you have this pinsformer.py. From there, you need to take this code. This util.py file must be there in your repository or in your directory, because we are gonna import this file from util import get clones. We'll be doing to have the number of layers duplicated because we want a sequence, the pseudo sequence generator concept which we saw before. So for that we need to bring this out. So make sure when you actually run this code, you have the code in the folder where you have this util file, and you need to update this path as per your actual code position or the place. We'll be seeing how to do that, but first let us understand the code. We'll import the torch. So basically, it is a Python language code, and they have importing torch, PyTorch for this tensor calculation, which is the best suitable. Then we are importing the neural networks. They have imported PDB for the debugging one, but we did not need it right now because it is not throwing error. But it's a good practice to do that. But this might be new to you for some reasons, so that's why I'm not going into detail of this. Then from util, I have shown you this util.py file. So this py file, util.py file, they are actually taking and taking some class from this, that is get clones. So once we go over here, you can see they might have this get clones function. So what it is doing is it is returning the module list. So we'll be going through this code part as well. So, but just remember that this util.py file needs to be in your directory when you run the Pinsformer code. That is very important. Else your code will show error. So the first function which they have defined is the actually class dot function, that is waveact function. We have seen that it is a linear combination of sine and cosine where different parameter weights which they have initialized with one, and then it will keep on improvising as it goes in the actual training step. So then it has a forward one where they return the self.w1 torch sin x, that is equivalent to w1 into sin x plus w2 into cos x. So that is what this class waveact function is returning. Next is the class feed forward. We need to go ahead in our architecture. We need to go ahead. Once you've given an input, you need some specific output. And for that, you need to have a forward pass. You need to go ahead with the hidden layers in neuron and the different architecture. So you need to go ahead, and that go ahead is literal terms, it's feed forward, and that's what it is being done. So you have this default parameters for feed forward, that is 256, and the model is your input parameters, like it can be 2 if it's x comma t, if it is x y t then it can be 3. That is again a hyperparameter. According to your problem statement, this would change. What they have done is, as you know, we have a normal sequential neural network. You have to learn the complex relationship, but that complex relationship or pattern would be brought up by this waveact function. But you have to go ahead, and neural networks, you could see, if I go to the neural networks basic diagram, you could see the sequence works default. If you wish to experiment with this default feed forward dimensions, you can definitely try changing the values, and let me know if you could get some different results. That would be interesting to see. So first you pass through the linear layers, the D model and default dimensions. Then you pass it to the waveact function, make a complex relationship out it. You induce a non-linearity, but in terms of sine and cosine waves. Then you again repeat the sequential flow. But you wanted to learn much more complex relationship. It's not just related to one-time complex learning. That's why you again pass it through waveact function. And then at final you have this third linear layer. Again, this could be experimented. I'm mentioning you again, you're gonna experiment with it. Try increasing layers, linear layers, to check results. If you're not getting any good results compared to the author when you run the same code with different hyperparameters, feel free to change this in sequential architecture to experiment and check if you could actually get something interesting and can lead to great research as well. Then you need to feed forward, you need to feed it forward, you need to pass it to ahead, and that's why you need to have this forward function. And what it should return linear, because you could say you have this linear one, then you have the waveact function, then again you have the linear one, you have the waveact function. So what it should return, it should return the linear one. So that's why you pass this and you return the final one that should be taken as an output when it passed through feed forward network. And when it goes after this, second thing, that transformer focuses on encoder and decoder. We have seen this multiple times till now that it basically focuses on encoder and decoder. So again you have the D model, the input, the heads. So you have a multi-head attention. Think like you're a student in a class, you wanted to check what's happening in your class. What will you do, guys? You guys will look here and there. Like this, oh, what this guy is doing, what this guy is doing. So you're trying to have attention over each other student to have an idea about what is happening in the class. Same needs to be for transformer. It needs to understand, if suppose there's a wave, how it will propagate ahead. It will need to have some past references, or not past, may not be the correct word, but a neighborhood, some instances it need to study so it can predict where it can go. And that's why you need number of heads. So like for example, I need to look around 4 to 5 students to know what's going inside the class. If it's exam time, I think 4 students would be enough to look into that, how much seriousness people are putting into paper. But if it's a game period, I need to have to look at many students to understand that what people are playing with. So that's how you can change the number of head. Again, this would be a hyperparameter. You have this built-in torch, that is multi-head attention. You need not to define it. These are already some things which could directly import from the PyTorch, and that is being used. So for attention, we are having this stands for neural network, multi-head attention, the embedding dimensions, the input one, that is the model, number of heads. Batch first is true. You can put it false as well. The main focus here would be the number of heads. This is something would play very crucial because if you increase the number of heads, the parameter count for the entire architecture would increase. Because what attention mechanism does is, if this is the one student, if there are four students, it would consider the impact of this student over this two and this one, to this one with this two and this one. So imagine if you increase the number of heads, so this combinations would increase, and that's why this head is a very important parameter when you try to deal with the resources over this. Then you have a feed forward. This would be called upon from here, the class feed forward, and you just put the D model, which was actually the criteria for the input one. Then you pass it through the activation function because you had a multi-attention. Then it learns the complex relationship, then it forwards that learning, induce more non-linearity, and then again go ahead. This is how this encoder layer block works. And then you have the skip connections over here. You could see that this attention one is being added again to itself. What is this? You could see this x2 is self dot act 1 dot x, that is the first non-linearity, that's the waveact function. Then it is x is equal to x plus self dot attention x2 comma x2 comma x2, first one, that is accessing the first one out of the index. You might be wondering that what exactly is this. This is like a residual connection. What you're trying to do is, when you try to feed forward, you need not to forget something that is learned before. When you take notes in your paper in a textbook, when you read a textbook, chapter 4 you are there, you won't forget chapter 1, chapter 2, chapter 3 for your exam. You need all those three chapters for your exam as well. Chapter 4 you have to study, but you can't forget chapter 1, chapter 2, chapter 3. That's why whatever you have learned in chapter 1, you revise it along with chapter 4. Whatever you have learned in chapter 2, you revise it along with chapter 4. Keep this adding. When you go to chapter 5, you revise chapter 1, chapter 2, chapter 3, chapter 4. And that is why it helps us to give an exam, understand whole picture. And that's how this residual connections are working. And that's why we are adding the previous information to new one. It's not the new learning only, it's remembering the past and learning something new. And that's how we go ahead in this architecture. So that is done by this encoder layer. Now, let us understand this decoder layer class. What encoder layer does is it learns the physics. And what decoder does is it tries to apply the learned physics. And if it is trying to apply the learned physics, so what attention mechanism can be used? What you can think of? This can be related with the cross attention mechanism. It would learn the physics, but who has learned the physics? It is the encoder layer that has learned the physics. And that's why we'll be using the multi-head attention. It will have an embedding dimension, number of heads again. But this, when we actually run this code and this Pinsformer architecture, that time, and in the encoder decoder layer, you will actually understand that this is actually a cross attention taken from the encoder layer. Then you prepare a feed forward model and initialize the waveact function activation 1, activation 2. Because when it's a sequential learning, you first have a linear relationship, then you pass it to the activation function to learn the non-linearity. And that's how it goes ahead. So the forward one, you pass the E outputs. What is E outputs? Basically, E output is your encoder layer output. So that is how the cross attention mechanism comes into picture. Whatever has been learned by encoder layer is now being used by decoder to predict something. So again, you have this connection over here where x2 comes from your decoder one. Consider this as a query input, and this key and value input that are E outputs come from the encoder layer. Then again, you pass a activation function over this x to learn the non-linearity and to have a smooth wave function, and then add again it to the x so that it doesn't forget what it has learned previously, and it keeps remembering what it has learned in past while keeping what it is learning in current way. And then you are returning this either to the next decoder layer, or you can actually put the output of this. So this is the use of decoder layer. Now, this encoder layer and decoder layer, this was just layer, but we are building encoder and decoder. How this will be used in the encoder and decoder function, let us see. For that, you'll have to define two class, that is class encoder and class decoder. Now, from the utils.py, you have imported this get clones function, and that's why the util.py file is equally needed. So now you define the number of layers, and then you define the forward function. For same decoder, you define the number of layers and a forward function. And then the operation is being performed, and then entire this would be clubbed into our Pinsformer architecture. Now, since we have covered encoder layer, decoder layer, then webAct function, feed forward network function. Now let us go at the main decoder encoder block. So what it will do is you have an encoder layer, but you need to stack that layers. You need to stack layers, encoder layers to form an encoder. You need to stack decoder layer to form a decoder. And that's what basically class encoder and decoder does. What it does is it takes the number of layer n and it clones it. This get clone comes from the util file, and that util file.py will see in some times. I don't want to change the tab because I want you to focus on this code right now. The heads you have specified before, number of heads, and that's how you duplicate that encoder layers and number of times. Then you define the activation function, that is wavelet, to bring out the oscillatory behavior in the wave equations or in the other PD equations. And then you have depth forward, that is the function forward pass, where it takes the each point in a layer, it performs the self attention, like multi-head attention. The self takes one point and it attends all other points. Then it transforms it using a feed forward network, and that it passes ahead and returns you something where it has learned the physics, because encoder learns the physics and decoder applies that physics. That what we have seen before as well. Now the code is much similar for a decoder and encoder. You could see it has self demodel n and heads. Same goes for here. Here it was x the shape. Here you could see you have e outputs. In if you see this one where it was q key and value, so query key and value, you could see actually it takes key and value from the encoder outputs, and x2 is the query that comes from decoder one. So that thing, because you are learning the physics in encoder, now what decoder does is it has a cross attention and it has to apply the learned physics, but from where it will learn? From the one which have learned, and the encoder is one which have learned. That's why you take e outputs from there. And then the only change that happens here is in the forward function, you add one more input parameter, that is e output. So, so you add one more parameter and the function, that is e outputs, and then you perform the same cross attention and give back the exact one step before the final solution. Suppose you wanted to give u of x comma t, then what you do is you provide the xt in some format where the next step when it processes to Pinsformer, you will get u of xt, and that's what decoder does here. And I hope you are now very clear that the activation function is used for what, and that's why when we have this all done, we transform or we pass it to the activation function. Now let us go for the Pinsformer code. At the start of this lecture, in the midway around, we have came across this snippet because I've explained the two snippets. First was one of the wavelet function, second was the class Pinsformer. So you need to have an output dimension, the D model, because you need to have the transform the input one to the longer dimension so that transformer actually uses it than the hidden one. This is again the hyperparameter and that is layers, encoder decoder layers, and then heads, number of heads. So what you do is you have a linear embedding where you transform your input to the much bigger dimensions that you specify as D model, and you so that you can actually use it for your transformer one, because two is not enough dimension for transformer to give accurate results or to actually make use of it. Then what you do is you pass it to the encoder, you pass it to the decoder, and then you try to give an output. And for giving output, you pass it to the sequential neural network model where you have the hidden layers. Then you again pass it to the activation function to induce nonlinearity. And here to learn the oscillatory behavior, which is generally found in a much of the PDEs. And then this again can be experimented if you want to increase the linear layers or not. That's up to you. And then what it happens is, then we have a forward, that is forward function, where x comma t, these are the parameters in the function. If you remember, we actually had a figure discussion before. So if you could see, we actually had this x comma t over here, and that is what is our input. That's why we are passing it to the parameter. We have the pseudo sequence generator, the spatiotemporal mixture MLP for transforming into linear embeddings. Then we pass it to the encoder, decoders, and layers. And then we have a output one, again the neural network output. So the forward function which we have used, imagine with this, and then we approximate the PD solutions. And that's what it is being done here. You actually concatenate x comma t because they are in pair, x and t. Suppose you wanted to see where the wave is propagating. So you need a position, you need a time. So x comma t. So you are concatenating it, and then you're reducing the dimension since you're concatenating it. Then you are making a linear embedding out of it so that the transformer actually uses it for learning when it passes through encoder decoder. So you pass it through encoder, the embeddings are passed. Now the physics is learned, but now you have to apply that physics which decoder does. But who has learned the physics? The encoder one. That's why E outputs will come again as an input parameter over here. And then you are returning the output, that is U of xt, and that would be returned by linear out. And that's how you return the output. So this is entire Pinsformer architecture and Pinsformer code. I hope I have tried my best to explain you the better clarity of this. If you still want to know about the detail in the dimensions, that with what dimension it started, at what step, how dimensions are changing, let me know in the comments. I'll definitely do that. And again, record a separate video if you want a much more detailed analysis of this architecture. But I have still tried to give you a very, very detailed idea of how it's done. I believe that since you have a code and understanding logic is very important. Once you know the syntax and once you know the language, to transform your logic into the code is easy, but only once if you know the logic. Though it's a tough task, it's not always that if you have a logic, you can directly just write down into code. That even requires a lot of practice and a lot of strength. But if your logic is not clear, you can't actually translate your logic into code. So that's why I've focused on making you make sure that you understand this logic. And I hope that is much clear to you. Now, let us see a practical demonstration. And in that, I'll explain you the utils file as well. We won't be going through detail for the utils file. I'll just explain you what this gate clone function does. And I'll explain you what other functions are doing in there, and then we'll do a practical implementation of this on the 1D reaction one. Now, I have opened this GitHub repo. I'll go to utils.py file. What I'm doing is I'll download this file because I want to run a Google Colab 1. I'll be running this 1D reaction Pinsformer 1. Let's get it downloaded. You're directly imported to drive and get it there from the Google Colab, but I'm preferring this for now. And I'll download the Pinsformer one as well. Yeah, pinsformer.py. There's three files I've downloaded. I'll download pins as well, just in case if that is needed, to be on safer side. That's, I think it's not included. They are not importing anything from that, but let's have it because there can be the case I might miss something. So, but firstly, I'll go through the util.py file. So this is for getting data. you need to have a data set to put an input, and you have x comma t. So what they create is they create a 2D dimension grid and they put it over the mesh, and that's how they generate a data, and they get the data along with the boundary conditions and initial conditions. This is for getting the parameters. You'll see how much parameters are. We'll check that when we run the code. Is a pseudo sequence generator, which we have learned before with the delta t plus t from x comma t to the further one, that is being done with this make time sequence. The get clones is nothing but the how much many times you need to repeat that encoder layer, how much time you need to copy that into a new layer so that you stack to format as decoder. That's what is get clones doing. And this get data 3D is for getting the data that is for the 3D PDE. So for the 2D you have grid, but for 3D you need to have a different code. So that's why this is for the 3D one, and they are expanding and they're squeezing it to get into proper shape. But if your PDE has the 3D one, make sure you get the data out of this. But if you had the 2D one, you get called the only get data function. So that is roughly the utils.py file does. So I have uploaded this all three. Before that, I have run this code once. I'll delete this to show you actual running right now. I'll delete this file. So we have these three files, that is physics informed neural network pins.py, pinsformer.py, util.py. I have downloaded from their GitHub repo and uploaded over my Google Colab. If you're using theirs cloning repository, then you might see this model.pens over there. Was this file pin.py is under the model folder. Yes. But in this case, I'm not doing that. I'm locally uploading. So here you could see I have removed that model and I'll run this. And then I'll change. I have changed CUDA 3 to normal CUDA so that I don't face number of GPU running out issue. Then I could do this. Then get n parameters. This parameters you can actually get it from the util.py file. We had a function, and that's why the parameters when you have n is 1, d model as 32, hidden as 512, and number of heads are 2. That time you get almost around 453k parameters count. And then let's run this. And probably it will start from 18 minutes or 17 minutes, but by the end it would make sure that entire this 1D reaction runs around 4 minutes, which is very, very feasible. And then let's see what loss value we get. Now I have completed a training part. You could see it took 4 minutes 38 seconds around. It was for 500 epochs or 500 iteration, whatever the word you prefer to. You can change this as well if you want to experiment with results. And the loss value which I get is very good. The boundary loss is almost zero. Initial condition it's 0.00001. The residual loss is very low. Overall training loss is very nice. I think somewhere around 5 into 10 raised to power minus 6. And if I go to their exact notebook, they get uh, 3 into 10 raised to power minus 6. That's the error loss they get. And now let us see actually how this loss is signified. Because if I take this, the predicted solution, the relative L1, L2 error are 0.012 and 0.024. And I guess for them it's 0.015, 0.03. And we are probably good with the L1, L2 error as well. The basic understanding of this would come us with the plots. The predicted one should match with the exact one, and the error plots should show minimal error. So if we go here, the predicted one seems like this, and exact one is like this. You could see there's almost match between the predicted and the exact one, and the absolute error that there's you could see the dark blue wallets. It signifies the very, very minimal error, and the yellowish part signifies a little higher error. So at the boundary part here, not boundary but in the graph boundary, not in the actual boundary condition of the problem statement, you could see there's some error, but the most of the part, this one where there's an exact match with the solution with the predicted one, there's absolutely dark blue. So which signifies that there's very, very less error. You could see this as the advantage of Pinsformer architecture. By adding the attention mechanism over the pins, you could get the predicted that matches with exact with less error. And the time it took was pretty okay. And you tried on T4 GPU and let me know if you could get same results. And if you're not getting same results, keep trying. It may not be the case that you get exact same values. You probably may not get it at first run it twice, thrice, or change the hyperparameters and try to run it again. But the code is working well, the ideology is clear. You'll need to play around with the parameters to match the results, which is again one of the important skill that ML practitioner must have. And since we have done this, now you could let me know if you have any questions or feedback for us. We'll definitely try to implement that. If you have some idea about extending this work, or if you have some curious idea of intersecting this with any other domain, you can drop us email at hello@visora.com. We'll see your application, and if your idea sounds good, we'll definitely try to collaborate with you. You could tag me in that email as well. And if you like this video, let us know, because we this was first time we experimented with managing two different fields and explaining that algorithm like SciML plus GenAI. And if you are loving this series, then let us know. We could definitely explore much more algorithms that are at the merge of intersection of two different fields. And we'll try to explain those as well so that you might work better in different domains. If you have any feedback for us, drop us in the comments, any questions, any suggestion, or reach out to me via LinkedIn. I know many of you are waiting for my CI/CD part 2. Once this is done, I'll be soon uploading that. Trust our efforts. I'm trying to manage that as well. I'll soon upload the part 2 of the video. This I thought should be a priority, and that's why I made this first. And then I'll go back to that CI/CD part 2. So see you there. And if you have any questions, or if you need such more videos for introducing new algorithms, let us know. We'll definitely continue this series as well. Thank you. Thank you all for being there in the long video, and drop us comments and let us know your feedback. Thank you.